Hi, everyone. Thank you all for joining us today for our last NUG call for 2024. We want to thank you again for joining us throughout the year. Today, we have a very useful and important topic of the day that we're going to focus on that is going to be best data practices. Again, my name is Charles Lively, and I'm a science engagement engineer here at NERSC. And I'm also joined by my counterpart, Lippy Gupta. And again, our role at NERSC is to engage and interact with our users and create a community of practice where we can share and scientific ideas and scientific research strategies. So on our agenda for today, um, keep in mind, we want things to be interactive. We have just a few simple updates and announcements about NERSC. And then we have our topic of the day, which is going to be presented by uh, three, uh, three very strong engineers that we have here at NERSC, Lisa Gerhardt, Lisa Klaus, and Steve Leak. But before we get started with their presentation, let's just dive into a few announcements. Okay, a few calls for participation and announcements that are going on. We do have the nurse user survey available. It should have been sent out via email, I believe, around November 10th. So please look for that. Um, and it will be, you will receive an email from the National Business Research Institute with regards to that. A couple of other calls for participation. The Platform for Advanced Scientific Computing has an open call for research paper submissions. The deadline for that is December 16th, and it will be held in Switzerland from June 16th through the 18th, 2025. Another important call is the DOE Computational Science Graduate Fellowship. That will be due, the application for that will be due January 16th, 2025. And the Department of Energy will host an informational webinar on December 10th about that as well. Okay, moving on to a couple of other trainings and meetings that will be occurring. We'll have a parallel computing with MATLAB hands-on workshop that will be occurring virtually on December 10th. We have a COCOS release briefing event also occurring on December 10th. Looks like that's going to be a busy day. And then we also have a webinar on high performance computing and software sustainability for green software development occurring on January 15th. It's a free registration, and this is a part of our HPC Best Practices series. Complete details, links, and more information about these announcements can be found in our weekly email, which we know you are diligently reading every week. Another important thing is that we will have a NERSC site-wide outage. It's been rescheduled for the week of January 27th, 2025. We'll make every effort to try to minimize that total downtime. Please refer to the weekly email for complete details about that outage and continue to check in the coming weeks if that changes. Okay. Did we have any questions or did anyone have anything to add to the announcements or calls besides what I presented? Okay, well, if not, then let's move on to more important and more interesting topics. And so at this time, I would like to turn it over to our counterparts, Lisa Klaus, Lisa Gerhardt, and Steve, to inform us a little bit about best data practices here at NERSC and what we should be doing with our data for proper data management.
All right. I will share my screen and I will also, we can get started with introducing ourselves. Thanks, Charles, for handing it over. I'm Lisa. I work at the user engagement group. And I'm a performance engineer. So my main thing is if you submit a ticket, you might get a response from me or a different consulting. And I'm also currently creating user videos. So we have a lot of documentation, but some users enjoy watching videos better than just reading documentation. So we also have an effort for this getting started. That's my main role currently at NERSC. And I can hand it over to Steve to introduce himself.
Hey, Steve Lake. I see a good handful of familiar faces and familiar names in the meeting here. So I'm in our storage team, particularly on the file system side. In the past, I was part of user engagement and was fairly regular in these meetings, and it's good to see people again. Lisa?
Hi, I'm Lisa Gerhardt. I'm in the Data and Analytics and AI group at NERSC. I'm also currently the acting data department head at NERSC, and I am very passionate about I/O and users' data movement and storage at the center, and I do a lot of work in that area.
All right. You should be able to share my screen. Please let me know if there's any issues. So yeah, you are lucky today to have experts like Lisa and Steve here in the room who can share you a lot about our best data practices at NERSC. This is supposed to give you a good overview so you understand more in detail how you're managing your data. And I will get started with this. Okay, so this is a very overwhelming graph that you can see here. And the purpose of this talk is to make this a lot less overwhelming and so you understand how Permature is connected to different parts and how you can make the best use of it. So what's like the most common workflow is that you create data on the Scratch file system, and we will go into every single system later on throughout the talk. So if you are not familiar with these terms yet, that's totally fine. Once you have this data on there, it's a limited storage. So for medium-term analysis, you want to move this over to CFS storage, which is the community file system. And then if you want to store things longer term that you do not need to access regularly, you can move that over to HPSS. The main thing you should take out of this slide and in general out of this talk that you should not forget is do not forget to manage your data. The data might get lost if you leave it on Scratch, for example, it might get purged and then you do not have access anymore. There's no copies there. So keep in mind it's your responsibility to manage your data, and this is what this talk will help you with figuring out how to best do this most efficiently. Okay, so what we will learn in this session here is you will get a good overview of the different file systems, the file storage systems, and which system is best suited for which use case or scenario. We will talk about data management mechanisms, best practices on managing your data. We will also show quick demos on available tools that we have that will help you with your data management. And of course, we have Q&A. Also, feel free to put questions in chat if they come up throughout the discussion here or raise your hand. But we also have a dedicated Q&A session at the end. Because this can be very overwhelming, even if you're already on NERSC for a long time, or if you're a particularly new user, there's a lot of acronyms. This is why we did provide this overview here. We don't need to go through it all right now. It's more meant as a reference for later on. So the slides are shared or should be already shared on our website. The main thing I would like to point out from this slide is we define I/O here as creating, reading, writing, listing, moving, copying, and deleting files and directories. So that's what we talk about if we use the term I/O. Then DTN stands for the data transfer nodes. These are optimized for data movement, and that will come up throughout the talk again. And then there will be a good introduction into DVS later on throughout this talk, but just so you have heard this term before, this is the data visualization service, and it's used as an IO forwarding service, which is very helpful it works by projecting a parallel file system like CFS or to the compute nodes. Okay. So a quick overview from a user point here. What's important, we have the Scratch file system, or referred to as perimeter Scratch. Every user has its personal space on Scratch. So this is not shared with anyone else. You have your dedicated space with a certain amount of usage there. And it's available to all perimeter compute nodes, and it's tuned for high performance. This is why we recommend using that storage area to run your jobs and store your data there. Then we have CFS, the community file system. Every project has a space on the community file system. So this is not a single space for each user. It's a shared project area, and it's meant for sharing data between user systems and also outside of NERSC. Then we have HPSS, which is the high performance storage system, and that every user has its own account on HPSS, and it's meant for long-term storage. You cannot access the data regularly there. It's not meant to access it frequently. We have home, which are most users very familiar with, because that's usually the first that you log into when you log into the system. You haven't changed any of those settings, and you have your personal space there, but that's very small, so you cannot store a lot of data in home, and it's also not meant. It's meant for storing just quick files there. And then we also have the global common file system, which is optimized for software installations and NERSC projects. Every NERSC project has an area on that directory in that. Okay, and now I can hand it over to Steve, who will give us a little bit of more details on.
Okay. I got this right. Am I sharing what I think I'm sharing? Does everybody see a slide called Overview of NERSC Storage Systems?
Yeah, but we
Yes,
see
we
the
also
presenter
see
view.
more.
I think we
It's the
see your
presented view.
speaker view.
Okay.
Yeah.
Let me try again. How's that now?
This looks great.
Cool. All right. So this is the slide you saw just a moment ago. So I'm covering my screen. Here we go. All right. So as Lisa was saying before, the most common data pattern, not the only data lifestyle pattern, but the most common one we see here at NERSC is that your data starts out on Scratch, usually generated by some job or series of jobs. Then you move it to CFS to share with your project team members. And then eventually after that campaign's finished, or you're no longer actively currently using that one, you put it to HPSS. So those are sort of also the three big file systems or big storage systems that we have at NERSC. There's a couple of others, but these are kind of the primary ones. Scratch is intended for data that's being actively computed against. CFS is configured and intended for data that is being used, being accessed, but not necessarily actually computed against, for analysis and sharing and so forth. And then HPSS is for important data that you need to keep long term. We've got data in HPSS going back, I think, more than 40 years. A general pattern that you'll see in data management is that you have different types of data storage, and as a general rule, there's a trade-off between performance and capacity. So a higher performance system tends to be smaller capacity, and a higher capacity system tends to be lower performance. So this is a lot of the reason why you need to actively manage data, because you want your currently active data to be accessed with the highest performance, and you want your large block of data it doesn't have as high access performance requirements. Okay, so another look at this this same diagram. Let's do a quick walk through it here, actually. If I go over here, all right, so up the top, this sort of top half of the diagram really represents Perlmutter. The key storage systems that we've got shown here, the Scratch storage system, which you can see is part of Perlmutter. It's very close. The arrows here are indicative of the kind of latency and bandwidth that you can expect to see from the storage system. So Scratch, great big fat pipe into Perlmutter. So very high performance. Down here on the left, we've got some of our file systems. So there's the home and global common down here, and CFS, which you can see is represented by quite a lot of disk capacity. And then we have our HPSS, which is a tape storage system. So kind of the short version of this talk is this list of dot points here. Almost all of your job I/O should be happening on the Scratch file system. Don't do I/O at scale on CFS. That's not what it's for. CFS is best for actively used data, but it's actually not the ideal place for source code. Source code and Conda environments are better off in global common software, or better still, actually, a container. If you're not using it for a while, bundle it up into kind of biggish tar files, ideally in the sort of hundreds of gigabytes range, and store it on HPSS. Home file system, you'll notice your quota is fairly small. It's really only meant for small scale stuff. Tests should really be your files, scripts, things like that. And this is really important. Make sure that anything important you have an off NERSC copy of. We have some systems that our systems are configured differently for robustness versus performance, and they do include some quite robust systems, but we don't have backups of everything automatically. We don't have an offsite data, what do you call it, disaster recovery, for instance. So it's up to you to make sure that you've got your own offsite backups of things. So starting out with Scratch, pretty much all of job I/O should be happening to Scratch. It's got a short, quick, fat path between the computes and a big, fast file system. Scratch is an all-flash file system. There's about 44 petabytes of space on it at the moment by default. Actually, we'll get into some details of this. By default, you've got a reasonably big quota. Importantly, it's what's called POSIX compliant, which is to say that you've got all sorts of features such as parallel I/O and file locking. This is very important when you're doing things at scale. It's intended for short-term storage. It's not meant for, this is not where you keep your data for a long time. In the next slide, we'll go into a little bit more detail about why. We've got two columns here, and you can kind of view them as pros and cons in a way. On the positive side, Scratch is pretty big. By default, you'll have a 20 terabyte soft quota and a 30 terabyte hard quota. What that means is that you can go over the soft quota. Once you're over the soft quota, jobs won't start, but your job won't actually fail. If you go over your hard quota, though, then the write will fail, and the job will probably fail. Scratch is fast. It's very, very parallel. It's got hundreds of parallel disks, basically. It's all flash. It has an aggregate bandwidth of something in the order of 6 terabytes per second out to the compute nodes. it's full POSIX, so you can do parallel I/O, MPI I/O, ACLs, which were mentioned in that glossary slide earlier. It stands for access control lists. This way you can control fine-grained control over who can access what files. Scratch handles both big and small files pretty well, and it handles I/O operations pretty well. So it's lots of positives there. A few limitations to be aware of though. It's big, but it's not huge. So you've got by default a 20 terabyte quota, but a full scientific data set can be hundreds or even thousands of terabytes. So you're not going to be putting your whole data set on there. You're going to be putting segments of it that you're currently actively using, and it's intended for I/O. It's intended for working against, not as a place to store your data. We don't have any kind of a backup for Scratch. Once something is deleted, it's gone. It's not like Windows where it goes into a trash folder. If you delete it, we can't get it back. Also, if something happens to the Scratch file system, we don't have a backup of it. So it's vulnerable to disasters. You need to make sure you've got a copy somewhere else. Move your data off it once onto another system once you've finished actively computing against it. Moreover, we actively purge it because it's relative to some of our other, it's big, but it's still finite in size. We have something in the order of 10,000 users at NERSC. Everybody needs sort of a bit of space on Scratch for running their jobs. So we actively purge data that has been sitting around for a long time, particularly that hasn't been used for a long time. Not a good place to be leaving your data sitting around, meant for computing against. A few tips, it's really parallel. You can use striping. There's a link here, which I think the slides have been published. This QR code also goes to it with some striping recommendations. You can basically tell the file system that things in this directory you would like spread across a certain number of disks in parallel. The default is that it writes to one disk at a time. That way it handles small files pretty well. And we've got some helper scripts to set up stripe sizes according to whether you've got you're expecting to see small, medium, or large file sizes in that directory. You can also manually query it. You can set it on a directory level. If you set striping on a directory level, new files that go into that directory get that striping. And if you copy files in, they'll get that striping, but the existing files won't. You'll need to do a copy back and forth to restripe them. They're physically already on the disk and whatever striping they had. Okay, this TLDR list you'll see a few times here. If it rings a bell, it's the same list that we went through just before. So we just talked about Scratch. We'll talk a little bit now about CFS. So CFS is for data. Scratch is for I/O. CFS is for holding data. It's a capacity-oriented file system. It's quite huge. Its current configuration has about 115 petabytes of usable space. It's very robust. A lot of things have to go wrong for CFS to break. However, it's further from the compute nodes. It has a much longer and more indirect path. So it's not really suited for job I/O at scale. A little bit more on that. So it's huge, 115 petabytes at the moment, another 33 sort of in the pipeline. It's very robust. So as well as the file system itself being very reliable, on CFS we take a daily snapshot. So that's basically what the file system looked like at some point during the evening of each day, and we retain these snapshots for 7 days. So if you accidentally delete a file, you can go into your hidden snapshots directory, just cd .snapshots in your home your CFS CDIRS directory, and you can see the state of your files for each of the past 7 days. You can recover from errors that way. We don't purge it. It, has quite good accessibility and uptime. It's pretty flexible. So Scratch, each user gets an individual space. CFS, each project gets an individual space, and that project space can be split into multiple directories with separately managed quotas that the PI can what do you call it? Can adjust. And Lisa will go through some details of that fairly shortly. We've got some tools for working with it, data dashboard. So CFS is also full POSIX, but that's when it's sort of directly mounted, which we do on the login nodes and on the data transfer nodes, but not on the compute nodes. And again, Lisa will talk a little bit more about this. We mount it over a service called DVS. The flip side of this is it's configured for capacity rather than performance. It's still pretty performant, but it's not at sort of Scratch levels. It's also configured with quite a large block size, so it's optimized for big files, but less well optimized for small files like source code. It's not directly mounted on the Perlmutter computes. It's mounted via the DVS IO forwarding service. Yeah, and that has a few implications. Yeah, one of which is it's not great for IO at scale. And we take snapshots, but the file system isn't backed up. So we don't have a second copy of the data somewhere. So if it's pretty robust, but if something does happen, we don't have another copy of it. So you do still need to keep a copy of important stuff somewhere else. So at this point, we've got some tools and mechanisms for making data sharing easier. And Lisa is going to run through them and I think demo a couple.
That's right. Thanks, Steve. So if you don't mind if I share, I get to see not one, but two share transitions during this talk. So just pushing it. Okay, so one of the common things, since like Steve mentioned, CFS is allocated by project, and projects can get fairly large. One of the things that happens fairly often, or used to happen fairly often, is the directory that a project could use would hit its quota. And then you would kind of have to sit there and figure out who is using up all the space. And the only tool for a long time, the only tools we had was for someone to sit there and say DU and run through the whole thing and see which directories are what size, and hope you had permissions to see everything. And if you have 10, 20 terabytes, 100 terabytes, takes a long time to run through it. So what we have is we have a couple tools to help with this. So the first thing, just to make sharing easier and knowing who has what on CFS. So the first thing is this data dashboard. And so you can find this on Iris. You just go to Iris and then you navigate over. Let me find just go, what? Nope, okay. You go over here where it says reports, and it's here under utilities under data dashboard. It used to be on myNERSC.gov, but we're migrating all of those over to Iris. So you find them there. You can either go to myNERSC and they'll point you here, or you can go directly via Iris. And what this is it shows you the state of sort of your data on CFS at NERSC. And so the first little section is your personal files. So your home directory and your Scratch. So I'm logged in as me. So it's showing me that, I have a lot of stuff in my home, and here's my inodes. So I'm not doing too bad there. But then the second part is the part you would look at when you are trying to figure out who's using things in your directory. So this is the top level directory. I'm just going to scroll down to the sort of end staff one. So this would be the path on this on the file system would be global CFS CEDARS MPCCC. So you'd put in your project name there at the end. This is where you go to. And it shows you where you are relative to the space quota you have and to the inode quota. And if you exceed either one of these, you won't be able to write any more to the file system. You can still read and you can delete. You just can't add any more stuff in. And so let's say you get up in the morning and there's a bunch of messages on Slack that say, hey, I can't write to MPCCC, what's going on? You can come to this page and you can look and you can see who's using your space. And so there's the blue is the breakdown by space so capacity in terabytes, and the orange is by inodes. And there's sort of a bar chart that shows you who's using what space. And so you can kind of go through and be like, oh, hey, at least I'm happy I opened this for once. I'm number 2 in this one instead of number 1 in both of them, like I usually am. So you can go and say like, oh my gosh, Lisa, you need to go clean up because we're at our quota and you've got 20 terabytes on here. So can you please clean up? And then so you can sort of kind of figure out where all your space is going on a user level. We also do it on a group level for each one of these directories. And if you come in here as a user and you're like, okay, I'm using up all this space, where do I start? I don't know what's going on. There's this my files and directories, and it'll show you your biggest file in a directory. And so like, for instance, this one, I have this really big file on here that I put on here a little while ago, just so I could have something to demo when I do this. And it's 1.6 terabytes. So you could go and say, wow, this is some pretty good low hanging fruit. Also this thing called junk.dat, probably you could delete this or maybe archive it. And it'll show you the ones with the largest files, the directories that have the most things in them, that's the largest strs. And then the directories that have the most inodes in them. So if you need to clean up by inodes, you can know where you're going to go. And so this is made every day from the scans that we do on the file system. It digests them and turns this out. And when you come on here, you'll be able to see all the directories that you as a group member have access to. So you can read that information. So the other tool that we have that I just wanted to show really quick is also an Iris tool. And this is how we have this ability where you can actually have multiple CFS directories for a single project. So let's say you had a bunch of guys that were doing simulations and you had some other guys that were doing, I don't know, something else, sorry, simulations and analysis or something, and you wanted to control the quotas separately for those. You could actually request, make new directories here. So if you're the PI, you can roll over to your page, you can come in. So I just typed NStaff and I clicked on the storage tab, right? Probably people spend a lot of time looking at the CPU tab, but it's the storage tab. At the top, it shows you how much CFS space you have. So there's, our allocation is 14 petabytes. We've given out 11, we're only using 6. We used to have a bunch of sensor data on the system, and that's why we have this big buffer. We just haven't taken it away yet. And then you can look and see for all these directories, who's using most of your quota. So, and you can move around the amount of quota you're given here, but just by typing in there, and then you can just go click update quota. I'm not going to change any of these because I don't want to strand anyone. But the other thing you can do here is you can also say new, and you can say, I want a new directory, for analysis or something. And you click that, and then you can choose what group you want to have access it. So we want to have all of NStaff access it. We would select that. And that will, and who you want to have owner it, be the owner. And that will create this directory on the file system and then add it to this list here, and you can give it some quota. So that's a way that you can have individual quota control over who's using what space in your CFS directory. And then the last thing I just wanted to talk about is something that's PI specific. There's often a problem when people are trying to share data where they forget to make the permissions shareable. So if you're a PI or a PI proxy, you can come to this PI toolbox and you can say, hey, this directory, I want to make this group readable. So let's see, you can say like, okay, I want to make it read writable. And again, you can click it and the system will go off and do that to that directory. And this, you can look down here, it'll say like, oh, hey, I'm still thinking about it. And then when that finishes, it'll show up down here and say, oh, I'm done. And it'll say it either completed successfully or it didn't. And then it'll go off in the background and run through and adjust the permissions for all the directories. So that's a way that you can sort of make sure that all the data that you want to share inside of CFS is shareable and viewable by everybody. That's sort of the demo part. Now let's see if I can get to the slideshow and folks can still see my screen. Did I do it successfully?
Yep.
Great, thank you. Okay, so now I'm carrying on. So those are the tools we've made for making CFS sharing a little bit easier. now I want to switch gears to talk about how we connect CFS on our computes on Perlmutter. And we use DVS for that. And the way that we do that, it's a kind of a venerated system. It's been around for a while. It was developed by Cray. It's now owned by HPE. And what happens is we have a couple of intermediary nodes. They mount the CFS file system, and then they project it to the compute nodes. So it's a way that you can get scale out of a system that's not necessarily designed for scale for access by 10,000 parallel machines at once. That's why we deploy it here, because CFS is architected for sharing internally with groups and sharing externally on the web. But we know that users also, there are some cases where users have legitimate needs for accessing the CFS data on the computes. And so that's why we use DVS for this. So if you're on the compute nodes and you're reading from Homes, Common, or CFS, you're doing it via DVS. This is different from on the login nodes where you're doing it via native client. So you may sometimes see different behavior because DVS doesn't have all of the features that you would see when you access it via the native client. So it's been on our NERSC systems for many years, and it was deployed on Perlmutter in June of 2023. So you've had it around for a while, and you've been using it if you've been running on Perlmutter. So like I said, we use it because it can provide file system access to thousands of nodes. The other nice thing about it is when these nodes are here and there's an issue on Perlmutter, it protects the CFS homes and global common from being affected by that. And so, you know, when some of you may remember when we first deployed Perlmutter, there were quite a lot of issues with stability because we were trying to deploy it via native clients. And that means that the file system is very vulnerable to any kind of network issues that might occur on Perlmutter, and that can cause issues for the whole file system because it in order to maintain data integrity, it needs to wait until it gets a certain response from the client. So if you don't have some protector nodes in place, you'll end up with sort of system-wide freezes. Well, the file system waits for some clients to come back online. So that's the pro of why we put it on there. It gives us scale, it gives us stability. It does have some quirks. And we'll get more into that in the next couple of slides. But if you're trying to do just read-only I/O, we have some read-only mounts that should make things less painful. And then there's some features. It's not fully POSIX compliant. You can't do file locking. So that makes it, for instance, HDF5 very unhappy. And then also if you have ACLs on the node, it'll disable any benefits you might have from caching, which we do a lot of on these nodes to deliver performance. So, you can chmod the files all you want, but if you do set ACL, and you try to access that at scale, you're gonna take a big hit in performance because every single time you access that file, you have to go all the way back to the file system. It also doesn't allow mmap. So if you're trying to do file locking, you must have ACLs. You need mmap, you're going to need to use Scratch. So if you're running into those problems, please open a ticket and we'll be happy to work with you. So the way that DVS works at NERSC, we have 24 gateway nodes that serve as DVS servers. Each server can work 1,000 IO nodes threads at once. That means a thread is like a single request, like you do an LS on the file and you want to get the size of it back. That's a request. It has to go and talk to it. So, that limit of 1,000 is basically designed to be sort of the optimal value for the gateway nodes as we have them deployed. They have really big caches, and DVS really likes to cache data. So what it can do is cache data on the local gateway nodes on the client that you're accessing from. So from the compute node, it will sort of aggressively cache the data, which will dramatically improve the performance because every step that you don't have to take needs a faster access. So we have two service modes where it's deployed at NERSC. We have read-write, and that's how CFS is deployed. And basically, when that happens, when a file is created, the gateway server, the DVS server that's going to be serving it, is is determined then. It's basically based on the inode, which is a unique number that's made when the file is created. So when you're accessing a file, it's always, and it gets assigned to gateway number 3, it's always going to go through gateway number 3 via the read-write interface. There's also no caching because DVS is not very fast at pushing writes back. And so if you have caching on a read-write system, it can cause some very confusing and sometimes wrong data writes. So we don't have any caching there. So it's a way you can access the files, but it's not the most performant way. And then we have the read-only mode, which means that a file can be served across all the gateways. It'll stay in the cache for 30 seconds, even longer if it's not pushed out. And we have quite a bit of detail on our website about how to get the most out of DVS. So if you're thinking about this, you're going to do a lot of I/O against CFS, then please check it out. I just wanted to talk a little bit about the differences between choosing read-write and read-only, and how some of the things, you can do things that are pretty natural, but can unfortunately lead to you having some trouble at large scale for I/O. So this is a picture of, you've got a 100-node job, you've got a Conda environment, you installed it in your home. So you just did Conda create, and it created your Conda environment, and it just by default, it put it in your home. So this starts up, let's say you fully fill, these are on the CPUs and you're fully filling them. So when this starts up, all 12,800 processes all try to read global homes elvis.conda, where your Conda environment is. So there's no cache because it's read-write, homes is read-write. And when you go, so it has to be fetched from the file system by each process. And so then what happens, because this file is also, it's going through one DVS server, the one that owns it is drowning under the load, and then all the rest of your processes have to wait in line. Well, it serves that file out 1,000 in a batches of 1,000 at a time. And you can see this here, this plot is just a cartoon of sort of the load of what you see on the DVS nodes. And you can see here, there's one particular DVS node that's pegged at 1,000. And here it's just waiting, and it's just serving as fast as it can. And every other process has to sit and wait. So the job's going to progress very slowly. And depending, this is no longer true. It used to be that other jobs using the server would be impacted too. But what we do now is we go through round robin and serve all the processes. So even if you're fully queued up 12,800 processes back, other folks are still going to be able to get through the queue as well. On the other hand, if you look at this, if you use the read-only mount, like if you install in global common, each 100-node job is spread across all 24 DVS servers. The first one that gets it, excuse me. The first one that gets it actually gets cached on the DVS server. So they don't have to go all the way back to the file system. And the load on the DVS server stays low. And you can see there's a cartoon over here of what the load looks like. It's much lower, everybody's moving through. The job starts up almost immediately, and there's not a long wait. So in this particular instance with CFS and DVS and global common, choosing the right file system, putting your stuff on global common instead of in homes or in CFS makes a large difference at scale. And the other thing you have to be careful about is when I say scale, it doesn't just mean I'm running one 100-node job. Maybe I have 100 single node jobs, but because of the way the queue works, they all start at the same time. That's the same, it's going to cause the same issue on DVS. Scale is large concurrency in a single job or lots of small jobs starting at one. So we also have, if you do find yourself in a situation where you need to do lots of read against data on CFS, we have a read-only mount, and it's actually a special path. If you're going to the normal path, global CFS seeders, that's actually the read-write one. We have another one that's DVS RO CFS, that's mounted read-only. So if you're going to be reading a bunch of data against CFS, then we definitely recommend you use that. So Scratch is always faster, but if your data is too big for Scratch, or you need to share with multiple people in your project, then you might benefit from looking at this DVS RO. Okay, so we talked about CFS. Now the next thing we're going to talk about is what to do with your source code. So we have a special, very small, dedicated all-flash file system called Global Common. It's dedicated for software installs. It's got a small block size. It's mounted read-only on the compute nodes, so you can benefit from the DVS caching. You get multiple DVS nodes. It's totally optimized for large-scale reads. When NERSC installs our own software, we put it on Global Common. It's especially good for Python conda environments if you're going to be using them all the time. And we've got instructions on our page about how you would get conda to create in Global Common instead of in your home directory. Python in particular is very hard from an IO standpoint because you end up in loading lots of modules, which involves traversing lots and lots and lots of directories in your LD library path and in your Python path. So if you ever do an strace on a Python process, there's a very tens of thousands of files get traversed for very simple Python startups. And if you're doing something inefficient for each lookup, that can really cause long delays for startup. And so the other thing to think about here is, in addition to if you do put your conda setup in Global Common software, it'll be a lot faster, but you should think about whether you want to have a conda environment loaded at login, especially one that is using your homes. Because when you submit a Slurm job, it's actually going to drag that information along with it. If Slurm pulls in a lot of stuff from your environment, it's going to pull in all that information about the Python paths and the LD library paths that are set by this conda environment, and you'll end up traversing those even if your job's not related. So, think about that if you put that in as login, so you can avoid accidentally doing more IO than you mean. I'm getting a little short on time, but I definitely want to say that, Global Common's performant, but we really recommend at scale that you put your software in containers. We have Shifter and Podman. They're very similar to Docker. It takes the file system out of the loop. And we have just a little chart here for the number of nodes and the startup time for Global Common versus Shifter. And you're getting almost a factor of 5 improvement of startup and orders of magnitude improvement over home for a container versus so containers are really the fastest way and the most stable way to load your environment at NERSC. Okay, and now we're on to talking about our tape performance system. Let's see. So see if this will work. Gonna mute that. So this is a view of our HPSS system, and at its heart, it's a tape archive. So down at the basement of NERSC, there's these really long cylinders of tape archives, and they go down, they're very large, and inside is just this little robot guy, and there's racks and racks of tapes, and when you retrieve it, the robot knows precisely where each tape is and goes and sucks it out and puts it into these readers over here on the left. So all data in HPSS eventually ends up on tape, but we do have a really big disk cache in front of it. So transfers initially go in very quickly. It feels a lot like a file system. But when you come to try and get it back out, you can run into problems if it's already migrated to tape. And that's because tape is linear media. You can't write anywhere. You can only append data at the end of a tape. Reading and writing is sequential. So if you want a file that's at the beginning and at the end, you have to spool through the whole tape. You can't jump around. And additionally, the robots have to fetch every new tape and load it into a drive. So when you're trying to retrieve a lot of data out of HPSS, it's actually the number of files that you're trying to get out that has a bigger impact on how long it takes than the number of gigabytes. So in general, if you put a bunch of data into HPSS and you're getting more than 100 files out, you need to do some special ordering to make sure that you're not hopping all over on the tape or putting a bunch of different tapes into the tape drive. And we have a helper script that can help you sort your files, and that's on our webpage. So generally for HPSS, you should think about storing your files as you intend to extract them. Like if you're backing up to protect against accidental deletion, maybe you want to use HTAR, which is a bundling executable that is part of HPSS to bundle up each directory. If you're archiving a data mirror, maybe you'd bundle by month the data was taken, or detector run characteristics or something similar. Just think about, what am I putting it in for? What am I going to do when I have to get it back out? And then try to size your bundles accordingly. Currently, the optimal size of the bundles is about 100 gigabytes, several hundred gigabytes. If you go larger than a terabyte, you're generally stretching across tapes, and it takes a long time, so it's prone to interruption. And when that is interrupted, you have to start all over again at the beginning. So you don't want to be too big. So a couple hundred gigabytes is really the sweet spot for that. You can also use the X for Q for long-running transfers. You don't want to do this on a compute because you actually don't get the full efficiency that you would get if you do it on the login nodes with the X for Q. And then when you're archiving your data, make sure your data gets archived. Like if you're running HTAR on a bunch of files, or you're running HSI put on a bunch of files, those are both commands that put files in HPSS. Collect the log info. Don't let it stream by on the screen. Like pipe it to a file and look at it later, because it will throw an error up and then it'll go on to the next file. It tries very hard to get your data in, but you can have errors stream off right off the screen if you don't collect them. Then you can also calculate checksums after the fact, or even during transfer, to make sure that your data integrity is intact. So there's a couple ways you can check on your HPSS usage. You can go to Iris and click on the storage tab for your account, and then scroll down. It'll say the HPSS archive, and it'll show you who has, actually this is for a project, this is for end staff again. So it shows everybody who has data in the project. You can go and look and see how much you have in there versus how much your PI has designated for you. You can also do this on the command line by typing show quota --HPSS. And if you're in multiple projects, you'll have different HPSS allocations for each one. And so it'll show you space used versus your quota for these guys. Okay, and now the last one is Homes. And Homes is there for holding configuration files and a few scripts, and for small scale tests, basically. So it is backed up. There are daily snapshots. So if anything is deleted, you can go into the snapshots similar to CFS and retrieve it. It's also backed up to tape, the whole thing, monthly. So it's there for configuration and scripts. It's not for large I/O. It just doesn't have the bandwidth to support it. It's also not intended for data storage. So if you are doing lots of I/O, you should use Global Common or a container. For your code, if you're storing a lot of data, you should use CFS or Scratch. And yeah, if you're doing conda environments, if you're going to do them in compute jobs, you should probably put them in Global Common. Okay, and then lastly, we want to talk about sort of data integrity. So it's every user's responsibility to manage their data. And that means inside of NERSC and in general for preservation. So at NERSC, there's different storage systems that are optimized for different parts of the data lifecycle. And when you're done with that data, when it's done with that particular part of its life, you need to move it to the next tier for holding it. And we have a lot of tools for helping you do that. And there's a whole section on managing your data on our docs that you can check out. Yeah, and I think that's it. Now I'll pause and see if there's any questions.
I see Stephen has a hand up.
Hi, thanks for those presentations. That was really useful. And the thing I learned was the my biggest files and directories thing under the data dashboard. I didn't realize that was there. That's really great. Is there any way that PIs can see the same information for their big users in their repos and or their collaboration users?
I mean, I think there should be. We'd have to do some designing to get the authentication part hooked up, but we've already done that for some of the other ones, so it should be doable.
Okay. Yeah, as you know, Lisa, on DESI, we've done similar views of the underlying data, but your view is much better. So I like your view to want to get access to it for our other users.
Okay, yeah. I'm glad to hear that. Yeah, I think we've talked offline about that. Maybe you could open a ticket. I don't know. I can't give a promise on the timeline, but that way we'll have it recorded.
Will do. Thanks.
Okay. Peachy?
Yeah, thank you very much. That's also very helpful for me. So I have one question or comment or desire that is any possible to Iris to make Iris include a tool for PIs to purge files in the CFS project directory if they're not accessed for a certain time period, or and also if they're so larger than certain size, because we project members' tendencies to put any important files in the CFS space, but then some members they change position, they even move to a different country without, of course, deleting or managing these data, and sometimes they lose access to NERSC. So in that case, then PI or PI proxy has to go through those click and in the PI toolbox you showed and change the group or authority and manually do something. So to change this tendency, I was even try to write script myself, but to move at least some file to old file to scratch space for somebody's maybe PI scratch space, but if there's a tool in the Iris, that would be also helpful, because every year, once or twice a year, we have to ask for requests to increase our either CFS space or shared scratch space. So that's sort of one kind of comment or or suggestion.
Okay, I'm definitely writing this down. Okay. Thanks for that.
Awesome. Did we have any other questions or comments or wish lists? Okay, all right. Well, awesome. Thank you, Lisa, and Steve, for a wonderful and very helpful presentation on best data practices. I'm sure everyone learned a lot. And with that, if there are no other questions, that concludes our last NUG community call of 2025. Wishing everyone happy holidays and wonderful new year. And we will be back in January for more community engagement fun. All right. Well, everyone have a great day and see you soon.
Thank you,
Thanks,
Kurt.
everyone.
Thank
Thank
you.
you.
Thank you.